Hello, I'm Jacob Verringer, and my partner is Gabe Cipollone. This is part one of our final project, and our topic was vectors in the plane, and I'm here just to give an introduction on vectors and explain the component form of vectors. A vector is something that has a direction and a magnitude. The magnitude is the velocity of an object and also the length it travels. And the direction is just the way in which the object is traveling, like which direction. A real life example of a vector would be a plane that travels a distance of 500 miles while traveling at 200 miles per hour and is heading west. It has a magnitude and it also has a direction, which classifies this as a vector.
So, just some basic information on vectors before we dive more into it. Quantities such as force and velocity involve both magnitude and direction, which makes it a vector. And they cannot be completely characterized by a single real number. To represent such a quantity, you use something called a directed line segment, which is something like this in a plane. The directed line segment is represented as this right here, PQ, with a vector symbol on top. And there is a initial point, which is P in this case, which would be here. And there is a terminal point, which is Q, which goes second, and which is here. And then it has a magnitude, and it is represented by this. So it's just a vector sign with the two bars. And this, you can find the magnitude by using the distance formula. So you would, to find the magnitude of PQ and the distance of PQ, you would take the first x value, the second x value, so the one of Q, the terminal point x value, you plug it in here, and then you subtract the initial point x, and then you square it, and then you add the 2, and you subtract it by the 0, square it, and you add them both together, and then you square root it, so you get 13. And you would do the same thing for this.
So now that we're done part one, and I'm done kind of giving an introduction and just the basics on vectors, we can now get into finding the component form of a vector. And this is important because before you start doing any operations or any work, you have to understand the actual form and the formulas of how to find the component form of a vector. So the directed line segment, whose initial point is at the origin, is often most convenient representative of a set of equivalent directed line segments. This representative of the vector v is in standard position. A vector whose initial point is the origin can be uniquely represented by the coordinates of just its terminal point. So to kind of explain, I have a pencil, and let's say this is point P and this is point Q. And point P is at 0, 0, the origin, and point Q is at, let's say, 2, 2. So then if you're explaining it, you would only refer to it by its terminal point, which would be 2, 2. And so you would not have to say the P, you would only just say the terminal point. You would not say the initial point.
So now that we have more information on how to find the component form, I'm going to show you how. So if we have 2 points, P and Q, and P is at 4, -7, the 4 is P1 and the -7 is P2. Same thing for Q. The -1 would be Q1 and the 5 would be Q2. So now to find V1, it would be Q1 minus P1, which would be -1 minus 4, which equals -5. And then to find V2, you would do Q2 minus P2 equals -5 minus -7, well, which equals 5 minus -7, which then equals 12. So V, which is represented as the component form, equals -5, 12. And you put them in these more arrow-like parentheses. And after you find the component form, which would be this, you would find the magnitude. And now, like I said earlier, you would use the distance formula to find the magnitude. But now, instead of using both values of the point, the x and y values of the 1 point, you would now use the 2 points of the component form. So let's say the p and the q. So you would plug in, you would square root -5 and square it, and then you would square 12 and then add them together, and you get the square root of 169. So that equals 13. So the magnitude equals 13, and the component form is -5, 12. So this might seem a little more complicated than it actually is. You're basically just doing the distance formula, but you're just putting another step right before that to find the component form. And so when you find the component form, you can just plug the 2 points in to the distance formula instead of having both coordinate points. And it honestly just makes it easier, and that's how you find the component form. And now that I have showed you how to find the component form and how to find the magnitude of a vector, I will be showing you some practice problems so you can try your hand at it and just see if you understand it. So here are 2 practice problems for you guys to try. You can go ahead, pause it here, screenshot, and then work through them, and then I will show you the solutions and work through them with you. So now to get into the solutions, for number 9, I decided to find the magnitude of V first, actually. So I took the terminal x, which is 4, and then I subtracted the initial x, which is 0, and then I squared that, and I added the terminal y minus initial y and squared it, and all of that came out to the square root of 17. And now I took the terminal x and subtracted it by the initial x and then squared it, which would be 16. Then I took the terminal y and subtracted the initial y, which is 1, and squared it, which would be 1. And so you add them together, and it's square root of 17. So because these 2 magnitudes came out to the square root of 17, that means u and v are equivalent. The 2 vectors are equivalent. And now for number 13, it's basically the same problem with different numbers, and now it doesn't give you a graph to kind of visualize and help you do it. It just gives you the points. So I did u first, and so what I did was I basically just did the same thing, just plugged in all the points. So I took the terminal x and subtracted the initial x, squared it. Then I took the terminal y and subtracted the initial y, and then squared it, and it came out to the square root of 90. Then I went on to v. So this equaled 9, and this equaled 81, and they added together to make 90, and then the square root's still there, so it's square root of 90. Now for v, I took 9, which is the terminal x, and subtracted the initial x, which is 6, and then squared it, so it's 9, and then I took the terminal y and subtracted the initial y, which would be negative 8 minus 1, which would be negative 9. Then I squared that, and it comes out to 81. So 9 plus 81 is also square root of 90. So since they're both square root of 90, same thing as up here, u and v are equivalent. So the vectors are equivalent.